So we will wrap up mass spectroscopy fragmentations in this mini lecture. If your head is spinning and you're feeling like it's still kind of voodoo, don't worry. A lot of mass spec is. We'll try to help you focus on the parts that actually sort of kind of make some semblance of sense. Alright, a quick recap from what we've already covered. Really, the most important thing you can do is figure out where is that odd electron located. That allows you to propose a structure for the molecular ion and gives you a starting point for your fragmentation mechanism. Once you've got that odd electron located, you can push electrons, draw electron movement arrows, and fragment that molecule in such a way that some kind of stable fragments result. What's stable? Well, you know tertiary is more stable than secondary, which is more stable than primary. And boy, delocalization of the charge or the radical beats everything. So, thus far, in the previous mini lecture, we looked at alkanes and pi electrons. Now, we're going to focus on those heteroatoms, oxygen, nitrogen. This applies to any heteroatom, sulfur, phosphorus, you name it. So, halides, ethers, alcohols, amines, carbonyls, all of them apply. And they all have the same kind of pattern. Once you kick out the electron from, recall that the n molecular orbital, the non-bonding pair of electrons, is the highest energy orbital. That's where we're going to kick the lone pair electron out of. So we can localize our odd electron on the heteroatom, and then we get alpha cleavage. So, for example, we'll look at this diethylamine. But before we look at the structure of the molecular ion, what big clue are you going to get from the mass spectrum of diethylamine? Well, it's going to have an odd molecular weight, an odd molecular ion. So remember the nitrogen rule. If it's an odd molecular ion, you're talking about a molecule that contains a nitrogen. So, hit it with 70 electron volts. What do you get? You boot that electron right out of the lone pair. So there is where you're going to localize your odd electron. Then what? Well, then it fragments to give you this. Can we write the electron movement arrows? Well, sure we can. Always put the tail of your arrow right there where your odd electron is, and it's looking for something to hook up with. So we go one bond over. And what does this tell us? Well, it tells us that we're going to have a big M-15 peak in the mass spec, and then we're going to be left behind with some charged fragment that's going to be detected, a C3, H6, 7, 8, 9, 10, 11. Whatever that adds up to, 36 plus 11 plus 14 should give me 61. So, if I suspect my compound is diethylamine, 1, I'd have an odd molecular ion at 73, and 2, I'd have a substantial peak, probably my base peak, at 61, which is equivalent to M-15, meaning I cleaved off a methyl radical. Alcohols, one tricky thing about alcohols is that they lose water very easily. So easily, in fact, that it's not unusual to have no molecular ion peak, which of course is very confusing. Maybe there's a weak molecular ion peak that is 18 units lower than what you suspect the molecular weight is. That's a pretty good hint that you've got an alcohol. Mechanism? How can this happen? How can I lose water in the mass spec? Well, basically you just need a molecule that's long enough. So for example, if we look at 2-heptanol, here is the structure of 2-heptanol, and as previous, we've lost the we've lost the odd electron off of the lone pair, so our molecular ion has localized the odd electron right on that oxygen. And then what? Well, then basically we convert the OH to a good leaving group by putting a proton on the oxygen. And how can that happen? Pretty easily. It's the six-membered ring transition state that's really quite facile. So basically it just reaches over and grabs that hydrogen from 1, 2, 3, 4 carbons away. That gives you the alcohol group, which now, the water, which now can, in a polar mechanism, that's why I'm making this a two-headed arrow, lose water to give you this species. Okay, well, what is this? It's a radical cation, so it can be detected at mass to charge 98, but it too can fragment. So it falls apart because this guy too can undergo that alpha cleavage to give you this radical cation at mass to charge 56 and the neutral fragment propene, which is lost for a mass to charge of M-42. So what we'd be looking for in the mass spectrum of 2-heptanol, and you might want to get on the NIST website and check this out, is there a fragment ion at mass to charge 98? Does that last long enough to reach the detector, or is primarily the base peak or a large peak at mass to charge 56, corresponding to a loss of 42? Well, check it out, see what's there. But the six-membered ring is kind of the magic cyclic transition state in organic chemistry. If you can get a six-membered ring transition state, it's very likely to take place. Alrighty, carbonyls. Carbonyls, same sort of deal. You got two lone pairs on the oxygen. So we're going to boot out one of the lone pairs and look for alpha cleavage. But there's another aspect of mass spec for these kinds of molecules, and it's called the McLafferty rearrangement, which we will go through as well. So 2-octanone right here, and as predicted, there is our odd electron. So we would expect to see an alpha cleavage. That's a pretty bad drawing. Let's try that again. We'll go on this side. Alpha cleavage here. Well, you know what that does. Spits off a methyl radical. And what it gives you is actually a pretty stable fragment. This is called the acylium ion. And it's resonance stabilized. So that pair of pi electrons can go back onto the oxygen, making it neutral and putting the positive charge on carbon. So this is a relatively stable fragment. And of course, this is what is detected. Something at M-15. But obviously, if I can do an alpha cleavage to the left, I can do an alpha cleavage to the right. And that would give me this guy. Again, this charged fragment is what's detected. This would be 24 plus 3 plus 16. So I should see a significant peak at mass to charge 43, amounting to the loss of this undetected 1, 2, 3, 4, 5, 6 hexyl radical. So those kinds of fragmentations are really super fast. If you have an aldehyde, well, of course, you're going to see a big time M-1 peak from the alpha cleavage of an aldehyde. I'll let you think about what would be a dead giveaway for an acid via alpha cleavage. Okay, well, this McLafferty rearrangement's the last thing we're going to go through. And you'll see that it's really quite similar to what we saw for the alcohol loss of water mechanism. So here's our molecular ion with the odd electron localized on the oxygen. I'm just going to redraw that, voila, so that again you can see that nifty six-membered ring transition state. When I say six-membered ring, I'm basically talking about 1, 2, 3, 4, 5, 6. Okay, I've got to get that atom in close proximity to the odd electron. So there's the hydrogen just ready and waiting to be abstracted. So that happens really quite readily. Now I have the protonated ketone and this radical right there, and what's happening next? Just the fragmentation. There's the cleavage, breaking that bond in half. So that's going to give me double bond here, radical, cation there. And what do I see? I see the charged fragment because of the positive charge on oxygen at mass to charge 58, and the whole rest of the molecule is lost at m-70. So there's lots of fun mechanisms to be had with mass spec. Again, 95% of the peaks we don't identify. We primarily use mass spec to confirm a structure. So we use IR for functional groups. We use NMR for really the carbon skeleton. And we use mass spec in two ways: to get the molecular weight, if we don't already know that, and to confirm by proposing rational fragmentation pathways. Alright, so at the end of all this, of course, I got to give you a joke, and this one's a pretty bad one, pretty much of a groaner. I don't know, I just thought I'd share it with you. So this poor guy, he went to the doctor's office because he wasn't feeling the greatest. And his wife says, "So how did it go at the doctor's office today, honey?" And he responds, "The doctor told me I have to take medication every day for the rest of my life." His wife says, "Well, what's so terrible about that?" He says, "He only gave me 4 pills. Yeah, definitely a groaner. I'll try to do better. Spur of the moment, okay? So, may you have many good mass spec medications as you work on your fragmentation patterns. Ay, 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 I'm calling this a wrap. We will see you in class.